course not.
Okay, all right. So it's my pleasure to introduce our next speaker, Antonio Mastro. Do I have it pronounced correctly?
Keep going. You're not done yet.
Antonio Mastroberardino. So sorry, I can't pronounce it like Pavarotti. I have no Italian genes in me.
It's okay.
I lived in Greece, not in Italy, so I don't have. Who's going to speak to us about mathematical modeling of HIV/AIDS epidemic in Cuba. So I've had the opportunity to hear his presentation in Cornell meeting in Ithaca at the New York Applied Mathematics Conference. So I'm happy to hear him speak with us. And speaking of repeated digits, sequencing once, so that will be your longest gap on today's, because he still has the longest last name out of any speaker. So I'm very happy to have him here speak with us.
Thanks, Mike. Thanks for inviting me. Okay, so this project was undertaken back in June of 2012 at University of Wyoming as part of a workshop on mathematical modeling in ecology and epidemiology. It's called the Rocky Mountain Mathematics Consortium. University of Wyoming holds this every June, and it's always on some different topic. And so part of the workshop is for all the participants to work on a project. There were about a half dozen projects. The one that I picked was modeling HIV/AIDS epidemic in Cuba. And it's actually a project that's listed in a SciAm book called Quantitative Methods in Math Biology by DeVries and others. Okay, so before I talk about the dynamics of the disease in Cuba, I want to talk about HIV/AIDS in general. Okay, and so it was first reported in the Morbidity and Mortality Weekly Report back in 1981. This is a report that's distributed to over 100,000 healthcare professionals. And it was reported that 5 men in Los Angeles had pneumocystis pneumonia with low T lymphocyte counts. Okay, so the T lymphocytes are part of the immune system, so their immune systems had been suppressed. Okay. The region that is most affected by AIDS is sub-Saharan Africa, with a prevalence of 5%. This region accounts for roughly 2/3 of all those that are infected and 2/3 of all those that have died from AIDS. The Caribbean region has the second highest prevalence. It's about 2%. Haiti and the Bahamas are at 3%. They're at the high end. And Cuba, of course, is part of the Caribbean. The middle bullet, as of 2010, there have been 60 million affected with HIV. There have been 30 million deaths. And I would say that at this point, you could probably add close to 10 million to those that are HIV infected, and probably 5 million to the additional deaths, AIDS deaths. In 2011, there were 34 million people that were living with HIV. That number has increased throughout the years, but it seems to be leveling off. Okay? The number of newly infected peaked in 2001, and it's on a steady decline, as is the number of AIDS deaths, which peaked in 2005. Okay? And so these decreases can be accounted for the number of AIDS deaths decreasing. It's due to the antiretroviral therapy that's working, and the fact that the newly infected number is decreasing is due to preventive measures. All right, so what is AIDS? Okay, it was first defined in 1983, and then every half dozen years or so it was redefined. Here's a definition that I'll give you. So someone has AIDS if he or she has fewer than 200 T lymphocytes per microliter. The normal count is 1,000. Or if the person has one of 26 various what are called opportunistic diseases. And so all of us have microorganisms in our body that a normal immune system can deal with. Okay? But if your T lymphocyte count is low, then these microorganisms seize the opportunity and cause harm. And so you can see the symptoms of having AIDS. And so this graph here that I have is a graph of virus count and T lymphocyte count. So you can see the red is the virus count, You can see in the initial weeks, you see a sharp increase in the number of HIV virus and a sharp decrease in the number of T lymphocytes. And then there's a sharp decrease in the number of virus with a small increase in the number of T lymphocytes. But then through the course of years, the number of virus increased steadily and the T lymphocyte count decreases until a person gets AIDS. All right, so the progression to AIDS. So I have, so reading from left to right and then down. So you see the virus on the left. The virus has these protein spikes which look like golf tees. When it encounters a T lymphocyte, the protein spike of the virus attaches to the CD4 receptor of the T lymphocyte. It has the appropriate key that will allow it to enter the cell. Once the virus enters the cell, the RNA of the virus is converted to DNA through reverse transcriptase. The DNA enters the nucleus, manufactures more virus, which exit the cell and then repeat the process. And in this process, the T lymphocyte cell dies. All right, HIV/AIDS in Cuba. So the first HIV infected was reported in late '85. First AIDS death was in April of 1986. The prevalence is now at 0.2, which is actually, back when I was reading these papers for this project, the prevalence was at 0.1 over a decade ago. But I think what's happening is that since people are living longer with the virus, the prevalence has increased. The transmission is mainly through sexual relations, and about 80% of those infected are men. And this is quite particular to Cuba. Okay? For example, in sub-Saharan Africa, the majority of those that are HIV infected are women. I think I read it was 58%. So you can definitely see a difference between the dynamics in Cuba and the dynamics in sub-Saharan Africa, and I'm sure it's different in all different parts of the world. Through Cuba's prevention program, they conduct 1.6 million tests per year. And just to put that into context, Cuba has a population slightly above 11 million. Okay, so it seems as though when I first thought of that, I said to myself, so they test 15% of their population each year. But then in reading more, I realized that there are some people that get tested multiple times a year. Okay, those that have actually had contact with someone that is HIV infected, that person is usually tested, I think, 4 times a year, every 3 months. In any case, that's a lot of tests. Cuba has 100% coverage for the antiretroviral therapy for those that have AIDS. And in 1983, Cuba initiated its program to control this virus. And just note that they started this program in '83. They didn't actually have someone that was infected until '85. Okay, so, and I'll discuss this program on the next slide. All right, so in 1983, Cuba established this National AIDS Commission in response to an infectious disease that was emerging in the U.S. and in Europe. And so I'll discuss, you can read the bullets, I'll discuss the main components of this commission. So in 1986, Cuba established the Partners Notification Program, which was established to, which implemented contact tracing as a way to prevent transmission. So anyone that was diagnosed with HIV, the person was interviewed, the names of sexual partners were taken, and those people were contacted in order to get tested. And so in my reading of these papers, it seemed as though back in around 2000, detection rate for contact tracing was about 30%, and I think now it's closer to 20%. In any case, that's a pretty high percentage for diagnosis from contact tracing. Sanatorium. Yes, Cuba did establish a sanatorium or sanatoria for those that were infected and those that did have AIDS. And so this was highly debated by, or I guess harshly criticized by other countries, that they actually quarantined those that were infected. And I mean, from Cuba's point of view, the point was to, number one, prevent transmission, and number two, to provide treatment for those that were infected. And in 1993, they instead of having, and the sanatorium were actually mandatory until 1993, and in 1993 became optional. Cuba established this ambulatory care system as an alternative, and so they had a choice of one of the two. All right, so on to the project. So back in Wyoming, this was the data that we had, and we were asked to fit this data and construct a model for this data. And I've actually added to the data for 2001 and 2002, but essentially this is the data for HIV/AIDS epidemic in Cuba. So we were asked to fit this data. There was one reference, which was a paper from 2002, and we found other papers that referenced that paper, in particular a paper by Rapatsky from 2006. And so we based our model on this 2002 paper by Arizosa and others, and a paper by Rapatsky from 2006. And so basically our model is going to be an SI model, where we take the I compartment, those that are infected, and divide that into three subcompartments, X, Y, and Z. So X are those that are HIV infected but undiagnosed, Y are HIV infected, diagnosed, and then Z are those that are diagnosed with AIDS. And so as I mentioned, these are the two papers that we based our model on. And so our model is different, and I'll just discuss the differences. The difference from our model with De Rozosa, they don't have a susceptible class. And De Rozosa and Lunes and a few other guys, there's a guy named C, they've written numerous papers on HIV/AIDS in Cuba, and their models never contain the susceptible class. It's kind of interesting because most epidemiology models have a susceptible class. In any case, our model has a susceptible class, which is different than the model by De Rozosa. The difference in our model from the one by Rapatsky is that we have an open system. Okay, there is a constant recruitment rate, the lambda, into the susceptible class, and Rapatsky and his colleagues had a closed system, which is kind of a way of rigging things. If you study SIR models, making a closed system makes the mathematics easy, but it really doesn't make sense physically. So there are notable things. The transmission rate is alpha. There's only one way to transmit the disease. It's from the undiagnosed, and this is due to Cuba's extraordinary policy of prevention. Okay. And there are two diagnosing terms: K, which is through the contact tracing, and K hat, which is through random testing. And so once we have the system set up, we computed the basic reproduction number, which is a number of secondary infections caused by an infectious individual that enters a fully susceptible population. This is standard procedure. So you can see that the basic reproduction number is given at the bottom. It is, so thing to note about the basic reproduction number is that for increasing recruitment rate to the susceptible class and an increasing transmission rate would increase the basic reproduction number, which should make sense. All right, the equilibria and the stability analysis of the equilibria. So there's a disease-free equilibrium. It is locally asymptotically stable if the basic reproduction number is less than 1, which is a matter of just looking at the Jacobian and looking at the eigenvalues. You can see the eigenvalues of the Jacobian are all negative except maybe the second. So all the eigenvalues are on the diagonal. And the second one is the only one that might be positive. And if you do some algebra on the second one, which I'm calling H sub 4, you can rewrite it as you see at the bottom, and of course if the basic reproduction number is less than 1, we have all negative eigenvalues, so we have stability. And it turns out also that the disease-free equilibrium is also globally asymptotically stable, and this was part of what we did, which was to prove that by using differential inequalities, and there was a proof by contradiction. All right, well, if the disease-free equilibrium is unstable, there's an endemic equilibrium point. And so the endemic equilibrium point is given by these equations here. And if you look at the quadratic and these coefficients A, B, and C, Y star will be positive if C is negative. And that's when R sub 0, the basic reproduction number, is greater than 1. And so we have a theorem that the system can have at most one positive equilibrium, and this is when the basic reproduction number is greater than 1. And as far as the stability of the endemic equilibrium, it's locally asymptotically stable by, based on just looking at the Jacobian. And we also proved global asymptotic stability by constructing an appropriate Lyapunov function and applying the Lyapunov's direct method. All right, well, as I said, part of the project was to fit the data and to run some simulations. And when we were trying to do this, remember this was a project that we had about 10 days or so to do, and so we didn't do anything rigorous as far as coming up with the parameter values. We just followed what was done previously. And so just comparing the values that we chose for our parameters compared with those that Rapatsky chose. And Rapatsky based their parameter values on de Rozosa's paper. I'm just comparing to Rapatsky. So we have lambda, which is a constant recruitment rate that the Rapatsky model does not have. And so we chose, that would be 100,000, which made sense, adding 100,000 per year to the susceptible class. Our transmissions rates are different. That was basically, as I said, we were trying to fit the data, and our value turned out to be slightly different. The one value that I would like you to look at is the mu, which is the natural death rate. So the one thing that we questioned about the previous models was the death rate that was chosen. Here the death rate is 0.0053, which means that the life expectancy of a Cuban, according to these models, is roughly 200 years. Yeah. And so that, to us, that didn't make any sense. A death rate of 0.02 makes sense. I mean, 0.02 would mean a life expectancy of 50 years, but the population that we're considering for this epidemic is usually between 15 and 50. And so if you think of the life expectancy of somebody that's already 15 to 50 would be about 50 years. So we think our death rate makes sense, whereas the other, the one from Rapatsky doesn't. In any case, in choosing 0.02, we then sort of varied our other parameters to try to fit the data. And so you can see that our k-hat and our alpha are different. Okay. And so these were the initial conditions that were chosen in running our simulations. And so using those parameter values, we fit the data from that table. You can see that fit on the left. On the right, basically what I did was I chose two different values of the basic reproduction number. In one case where the endemic equilibrium is stable, and in the other, the disease-free equilibrium is the stable point. So you can see the black and gray are endemic equilibrium, the blue and red are disease-free. All right, well, one of the participants, Ahmed, had the idea of applying optimal control to sort of deal with this, the sense that we got that these parameters weren't quite right. And so he knows about optimal control theory, and so what he and I have been doing over this past year or so is to try to apply optimal control. And so in optimal control, you basically add this function u, which is a control function with scalar functions u1, u2, we have three optimal control functions here. One for representing an effect from educational programs, condom use, another from contact tracing, and then another from random testing. And you can see how we insert them into the model. So the U1 is to decrease the transmissivity of the disease, right? And U2 and U3 are to increase the diagnosis. And the idea is to construct an objective functional and to minimize this objective functional. And this is something that I'm still not sure if this is going to be the case. As far as what the objective functional looks like, we want to minimize the cost of the of this control. So you see the u's all being squared, and that's standard. Basically, once you go to characterize the control, it makes things easier if you square the controls. And the bx term is basically we want to minimize the number of HIV infected that are undiagnosed through time. Okay, and we're considering t as an end time, capital T as an end time. And so applying this optimal control theory, we want to find optimal controls so that J is minimized over a set gamma of admissible control functions. Okay? And the standard theory goes like this. Existence is guaranteed since the integrand is convex on a closed convex control set gamma. The model is linear in the controls. You see that if you went back to the model, it would be linear in U1, U2, U3. And it's bounded by a linear system in the state variables. And this is mainly because we're fixing the end time at capital T. Okay. Well, if you apply Poincaré, I'm sorry, not Poincaré. See, I'm having trouble with a Russian name. Okay, it's Mondrian maximum principle, which is what's used to
I believe you
construct.
pronounced it correctly and better than I pronounced your last name.
Oh, sounds good. So it's this Pontryagin maximum principle that takes this idea of optimizing an initial value problem and converts it to optimizing a Hamiltonian function. So in order to come up with this optimality system, you construct this Hamiltonian function, look at the necessary conditions from this principle, and here are those conditions. So we have the state system, which is what the initial value problem was, okay, along with the initial conditions, which I don't have listed. And now we have this adjoint system. So this adjoint, so part of this principle is to insert these adjoint variables, okay, and that play the role of Lagrange multipliers, okay. And so now we have an adjoint variable for each of the state variables, and so we have this other system of 4 ODEs for these adjoint variables. And now, what's different about this adjoint system is that it's actually a final value problem. We know what the lambdas are at t, but not at 0. So this is, and then also we have this characterization of the control, okay, and like I said, this all comes from this principle. And I mean, this is certainly a non-standard system of ODEs. I mean, we have an initial value problem for 4 functions, and then a final value problem for these other 4 functions. And these equations are all coupled. So it's tough to solve, and there's this forward-backward sweep method where you basically guess your control, you solve your state system as an initial value problem, okay, and actually you have to get, it's basically an iterative process where you have guesses for your state variables, your adjoint variables, and the control. You solve the state system as an initial value problem, okay, and then you go backward and solve the adjoint system as a backward problem. Okay? So, and it's an iterative process until you gain convergence. This part we haven't quite done yet. We have a program, and I still need to get some time to run some simulations. And so this is an ongoing project. And so I'll end here and show you a list of some of the references. We did submit a paper without the optimal control part. And I'd like to thank my collaborators, Yuan Ji, Ahmed, and Hao, and also the organizers of this, of the Rocky Mountain Mathematics Consortium, who are Rong Song, Michael, and Dwayne. Thank you.
Well, let's thank Tony. Okay, I'd like to ask a question.
Sure.
Okay, I can understand, like, for example, if you're studying Sub-Sahara, it would make sense to have an open system because you have surrounding neighbors, but Cuba is on an island. Wouldn't it make more sense to have a closed system because it's harder to have external influence when you're on an island versus on a continent?
Well, part of being an open system is accounting for an increase in population.
Oh, I
That's
see.
really it. And the increase in population, it's rather slight, I'll admit. So you could justify a closed system, but just how you set up a closed system is where it just doesn't make sense. In that you're basically you're adding to the susceptible class a term that is basically the death rate times the population, which, I mean, it's kind of fudging things, really. But considering Cuba's population is growing, let's say, at 2% a year, it might be reasonable. But then again, I mean, HIV, this disease has spanned decades. So it should make more sense to have an open system. Even if it's just for one particular region, you're just accounting for an increase in population, assuming an increase in population.
Also, how come you only consider the spread of disease by sexual transfusion? Why not through the blood? If I'm not mistaken, blood contact also transmits
Sure, yeah,
disease.
that's a good question. It goes back to the beginning where I mentioned that 99% of the transmission is due to sexual relations. And this is a good question because this is also particular to the dynamics in Cuba. I think it's the case that in Eastern Europe, where there's a considerable level of transmission due to drug use. So in that case, you could have a compartment for those that are infected through non-sexual transmissions. And that's something that actually, we wrote down a system for that, but we didn't think it applied to Cuba, so we just didn't bother. But you could certainly subdivide these compartments further due to the way it was transmitted and some other ways of adding structure as well.
Gotcha. Okay. Other questions or comments for Antonio? Okay, let's thank Antonio one more time.